Hello, hello, hello. Hopefully everyone can see me and everything and can see my screen. Please let me know if you can't. And please feel free to say hi in the chat. I'm just going to try and get my chat sorted so I can see everybody. But how are we all doing? How's everybody? Please, again, feel free to say hi in the chat. It'd be nice to see those of you that are here who have been before, or if you haven't been before, welcome back to those of you that have. Welcome to those of you that haven't. So nice to have everybody here. Oh, thank you very much. It's very fluffy today. I think it's a bit humid. Hello, yeah, good, thank you. I'm very good. I'm very good. Hello, hello, hello. Welcome, welcome. Welcome to our A-level class. Can you let me know if can you see my screen okay? Can you see me okay? Is everything fine? My laptop was being a little bit of a pain at the end of that last class and it froze a bit. So hopefully it's all sorted itself out now. Yeah, fabulous. Thank you guys. That's brilliant. Okay, I can't see myself, so I don't know what it is that you guys can see because that Webclass, my screen is not playing properly, but I can see all your chat, so that's fine. That's all I need. Very good, very nice. Okay, cool. Right, we are running a couple of minutes late, so I'm going to get started as soon as possible. So hello to everybody. So I haven't managed to say hello to individuals, but really nice to have you all here for our A-level chemistry web class, YouTube class on the equilibrium constant. So it's something that comes up a lot in lots of different aspects of chemistry. We apply a lot of the principles that we're going to be talking about and reminding ourselves about here in lots of other parts of chemistry. So the principles that we'll be using are really important. So hopefully over the next kind of 50 minutes or so, we're going to get ourselves acquainted with the equilibrium constant and how to use it and things like that. So a little bit about me whilst I get my touchscreen sorted. I'm the lead, sorry, you can't see me now. I'm the lead chemistry teacher at SnapRise. I teach the GCSE and A-level chemistry class here at SnapRise. I've got a PGCE in chemistry education from Oxford, and I've been teaching A-level chemistry for the last 6 years. I love all the sciences. I am a fan of all the sciences, so chemistry, physics, and biology. But chemistry is my fave. And I do have a master's in chemistry, so that is the thing I know the most about, definitely. So just to let you guys know, we have still currently got 25% off our courses on the website. So I'm going to, at the end of the session, I'll finish a couple of minutes early, hopefully, and then I'm going to talk you through the amazing resources and content that we have on the website if it's something you are interested in. And if you fancy logging in and joining us, we've got classes and students that are part of our courses on the website. Then you use the discount code BACKTOSCHOOL21. It gives you 25% off your first month, so you can have a go, see if it's the thing for you, come and join us. And yeah, you will need to use the code BACKTOSCHOOL21 if you go to the SnapRise website, but I will show you all that's on offer at the end, hopefully. Okay, so our objectives for this session for the next 50 minutes or so are to understand the quantitative assessment of the position of dynamic equilibrium. So it sounds really wordy, but it basically means how do we define with numbers where the position of equilibrium is in a dynamic equilibrium. So that's what that is. We're going to look at working out the units for the equilibrium constant, which often sounds terrifying, but is a very simple process. And then we're also going to calculate the equilibrium constant, calculate a value for the equilibrium constant from initial and equilibrium concentration. So you might have seen this as, or recognize this as, the ICE method. So we'll be doing a little bit of that hopefully at the end. So I'm going to need to speed through the content to make sure we've got time to spend on the GCSE, on the exam questions. What we're not going to look at is heterogeneous equilibrium, which is something that year 13 need unless you're an EdXL, in which case you don't need it. Okay, so just to have a look, these this is the specification. I always say this, the specification is so useful for everyone, GCSE, A-level, whatever. It's so useful because it's basically a checklist of everything you need to know to get a grade in your A-level. It's everything that the exam boards want from you. So this is what AQA specifies. This is what the specification is for AQA students on the content that we're doing at the moment, the KC. This is OCR. This is the specification from OCR. Note that learners for OCR do not need to determine the units for KC. So if you're an OCR student, you won't need to do that, although it's actually relatively easy if you're good with rearranging things. So you might as well have a go at it anyway. And then EdXL, they are very brief in what they expect from you, but it's still the same stuff. So notice that you will notice if you compare the specifications, they're very varied in how much information they give. Sometimes EdXL gives you loads of information and AQA gives you 2 lines, and sometimes EdXL gives you 2 lines and AQA gives you loads. It's varied, but it's really useful. So please have a look at what is expected of you. So we cover all 3 exam boards vaguely, and if there's major differences between them, we do try and tell you. But if you have any questions, please let me know and we can try and chat through it if we have time. We just notice here that it says about heterogeneous as well, so we're not going to look at heterogeneous expressions in this exam board, in this session. So what do we already know? So hopefully from GCSE / from earlier in our A-level, we are aware of what a dynamic equilibrium is. So do we know what dynamic equilibrium is? Good question. So this will be mainly the year 12 content for equilibrium, but we will touch briefly on some of the equations, calculations that you need to know for equilibrium for year 13, because you still need to know it at year 13, but we're not going to look at KP or KA or anything like that. So just KC, just equilibrium concentration equilibrium constant. Oh, lovely. Yes, and we will be looking at Le Chatelier's as well. Fantastic. Well done. So is when the forwards and backwards reaction occur at the same rate. And when does this happen? So it is in a reversible reaction, but when not every reversible reaction, there's a specific environment. There's something we need about our reversible reaction in order to establish a dynamic equilibrium. Can't just be a reversible reaction, it has to be in a closed system. Well done, guys. Yeah, exactly right. So in a reversible reaction, dynamic equilibriums occur in a reversible reaction when the rate of the forward reaction is equal to the rate of the backward reaction. And what does that mean for the concentrations of concentrations of reactants and products? They are the same. Good. So the rate is equal to, notice we use equal to, you can use, say the rates are the same when the rate of the forward reaction is equal to or the same as the rate of the backwards reaction. And it's in a closed system. Has to be in a closed system. We can't have matter leaving our system. And it means the concentration of the reactants and the concentration of the products stay constant. They stay the same over time. They're not same as equal to each other. They're not necessarily equal to each other, but they stay constant over time. So constant, I think, is a better word to use when talking about the concentrations, and the same or equal to is fine for when we're talking about the rate, because the rates of the forward and backwards reaction are equal. They are the same, but the concentrations of reactants and products stays constant, stays the same. So for equilibrium, because it's not very easy for you guys to do in the chat, we do a kind of a 2 single half-headed arrow thing for our reversible reaction. It means we've got a forward reaction and we've got a backwards reaction. And when we talk about concentration of something, we use those square brackets. Hopefully this is something that's not new to you. What does a homogeneous mean though? This term homogeneous, what does it mean? A homogeneous system or a homogeneous reaction? What are we talking about? The reactants and products are what? Good. They are the same state or phase. Yeah, good. So homogeneous means a homogeneous reaction means reactants and products are in the same state or phase. So they're all dissolved, or they're all solid, or they're all liquid. Good. Fantastic, well done. Okay, so hopefully using this, hopefully we're all solid on this, and then we can move forward. So part one then, the equilibrium constant. Let's look at the equilibrium constant. So quantizing, making a number, making easy to quantify using numbers, the position of equilibrium. So the position of equilibrium can be described quantitatively, as in with numbers, using the concentration equilibrium constant, Kc. So capital K, small c. So A plus B makes C plus D. These little a, little b, what does that describing? Little c, little d, what am I describing there? What are those? Good, it's the moles of each, it's the stoichiometry, it's the relative ratio of those different reactants in the balanced chemical reaction. So those are the number of moles usually, or it's just the ratio of our reactants and products. Good. So how do we write our expression for Kc? Anyone know how do we, if I had this expression here, how would I write this equation here? Sorry, A plus B makes C plus D. How do I write Kc? How do I write the expression for Kc? Yeah. Fantastic, really nice, very descriptive as well, Georgia. Good. So good, it's our products to the power of their moles or stoichiometry over reactants, again to the power of their moles. So in this case, good, yeah, it needs to be in square brackets. It would be products first, so C, capital C to the power of little c, might be 1, so it might be the power of 1, so we might be able to leave it off. We might not need to put little c up there, but it might be a 2, so we might need to put a 2 in, times by, so I can just write them next to each other, it means the same thing, times by the concentration of big D, whatever D is, whatever chemical D is, to the power of little d, however many moles of it we've got, divided by concentration of A to the power of little a times the concentration of B to the power of little b. So again, sometimes our little values might be 1, so we might not need to write anything, but they might not. It might be important. Okay, so if our value for Kc, if our equilibrium constant is greater than 1, what does that mean? What does that mean? If our value for K is greater than 1, where is our equilibrium? Any ideas? So I think I was saying greater than 1, wasn't I? Which I don't know if I meant to do, if I was supposed to be doing that, but so I think I said if it's greater than 1, if it's greater than 1, then concentration of products must be greater than the reactants. Good, so we've got a bigger number on the top and a smaller number on the bottom, which means the concentration of products is greater than the concentration of reactants, which means our equilibrium must be towards the products. So equilibrium, if K is greater than 1, equilibrium is or lies towards the right. Fantastic. I think I said greater than 1. It looks like that's what you guys have answered, so apologies. Let's go back to less than 1. What happens if it's less than 1 then? If it's less than 1, if the value of K is less than 1, then what do we know about our values or amounts of products and reactants, and therefore where is the equilibrium? Good, well done. Fantastic. So it must mean that the bottom of our reaction, of our equation, of our fraction is bigger than the top. So if the bottom's bigger than the top, we're going to get a number smaller than 1 because we're going to get a fraction. So like a quarter, a third, an eighth, a 16th, whatever it is. So we're going to get a fraction smaller than 1, which means we must have more reactants than products. So it must be lying over to the left. And what about if they're equal then? Oh, that's horrible writing. Let's write that again. What about if they're equal? What if we have, if the numbers or concentrations of top and bottom are equal, then equilibrium is in the middle. Good. It lies exactly in the middle. So it's exactly halfway between products and reactants, because if the values of the top and the bottom of the equation are the same, then the equilibrium must lie halfway. It doesn't shift at all. Yeah, exactly right. Good. Fantastic. Okay. So hopefully we're used to, or we have had practice writing KC. Let's put it into practice with an actual equation now, not just A's and B's, and then have a go at writing the units. Although you don't need to do the units if you're at OCR, but it's not that difficult, so it's worth having to do that anyway, I think. It's good practice for doing units. So the units of KC depend on the molarity of reactants and products. It means how much of each we've got. So for KC, what's the expression for KC? If I ask you to write the expression for KC, the equilibrium constant for this reversible reaction, what would we write? I know it's not that easy to write when you're typing because you can't do the uppy downy bits, but have a go, give it your best shot. How do we write the equilibrium expression for KC for this reaction here? What do we need to write? We do products over reactants. So we need to do concentration of products to the power of whatever it is over concentration of reactants to the power of whatever it is. Oh, very nice. Lovely. And then we're going to have a look at doing our units as well. So let's just write the expression for KC first. So it will be SO3 gaseous. Concentration of SO3 to the power of 2, because it's got that 2 there. It's molar amount. Its stoichiometry tells us we need 2 SO3, so we've got to square it. Over the top of products over reactants. So our reactants, we've got SO2 to the power of 2 times by O2. Oops, didn't put my gaseous symbol in, sorry. Times by O2 gaseous to the power 1. So we don't need to put a number next to my O2. Is it a must to write state symbols? No, it's not a must. They obviously, if they've asked you to include state symbols, then definitely include state symbols. Technically, you should be including state symbols, but if it comes to an exam, they are. I'm not sure I've ever seen it where they've deducted a mark for not having state symbols, but better to do it. You might as well, the information is given to you, so it's just remembering to write it, that's all. Good question. So then if we want to do our units, the best way to do units for anything is to sub in the units for the equation that you're using. So the equation here, we've got concentration squared on the top. So if I write the units of concentration, hopefully we all know it as mole per dm cubed, or mole dm minus 3, and it's squared because that's what I've done to my concentration on the top there, divided by, and then I've got mole per dm cubed squared on the bottom again as well, but I've also got another mole times by another mole per dm cubed. So that makes it nice and easy. All I've done is I've subbed in the units for the things that I've been doing in the equation, and then I can cancel. I can see I've got a mole per dm cubed divided by mole per dm cubed. So they cancel each other out. It's like x divided by x, a divided by a, 3 divided by 3. They cancel each other out. And I'm left with then 1 over mole per dm cubed, because I can't have 0 on the top. I've got 1 on the top. So 1 over mole per dm cubed. Or if I write that kind of properly on one line, which we should do, it then becomes mole minus 1 dm cubed. Sometimes we like to write our positive powers first. So we would write dm cubed mole minus 1, because technically, mathematically, that looks a little bit better. But you don't have to. You can write mole minus 1 dm cubed and you would still get the mark. Why is it 1 over? It's because it's a fraction. Yeah, exactly right. We can't just remove the fact that this is divided by mole per dm cubed. It's whatever that value was divided by mole per dm cubed. So we can't just forget about the fact that it was divided by mole per dm cubed. So in order for it to be something divided by mole per dm cubed, we put a 1. Yeah, exactly right. I like how you said that there. There's like an invisible 1 there. It's 1 times the top. And we've cancelled those units. So we've just got 1 on the top. That's nice, yeah. Nice way of putting it. Okay, same thing for the bottom one then. Can we do the same for the bottom? Can we work out what the units are going to be? So if we write our expression for KC, I'm just going to speed write it because I want to make sure we've got enough time at the end to do exam questions. So again, products over reactants. You guys feel free to go ahead. Well done, those of you that already have, and work out what the units are. So products over reactants, so it's HI gaseous squared because of the 2 over reactants, which are H2 gaseous to the power of 1, so we don't need to write anything, times by concentration of I2 gaseous, again to the power of 1, so we don't need to write anything. So that's our expression for Kc. Lovely. Now we can sub in our units. So we've got mole per dm cubed squared on the top. And we've got mole per dm cubed times mole per dm cubed. I could put them in brackets if I wanted to. So yeah, well done, those of you who worked out. That means we've just got mole per dm cubed times mole per dm cubed divided by mole per dm cubed times mole per dm cubed. So they cancel. So I end up with no units for Kc, and that's perfectly fine because they are entirely dependent on the reaction that's happening, on the reaction that we're working out the equilibrium constant for. So, whoops, there are no units for Kc, and that is O. Okay, how are we feeling about all of this? How's everyone feeling? Give me a 1 if you're feeling pretty confident and smiley face, or you can give me a 2 or a middling face if you're feeling it's okay, but probably going to need to do a little bit more revision on that, or maybe it was the first time you've heard it all, so you're a bit like still taking it in, or 3, oh my gosh, no, that was awful, I hate it, never mind. Oh, that was a good question, sorry, that I've just missed there. If there's no units for the second one, why do we have units for Kc, or does it vary? It does vary. Yeah, it definitely does vary for Kc. It's entirely dependent on the reaction. So our units will vary. Yeah, it's a bit of a weird one. It feels like they should always be the same, but of course, if you think about how we construct the equation, of course it's going to vary because it will be entirely dependent on what's happening in the reaction. Good, lovely, well done guys, fantastic. Okay, let's see if we can get through this question then. So at the moment, we are we're only going to write the expression for Kc for this exam question. So feel free to have a read through the information. The main thing says write an expression for Kc for the equilibrium. So that's the first thing we've been asked to do. And then we've also been asked to give the units. So write an expression for Kc for this equilibrium. The equation, chemical equation, is given above. So can we have a go? What would we write for the expression for Kc? It's exactly the same as what we've just been doing. This is just given to us in an exam question, in a past paper question. So what do we write here? Kc, capital K, small c, is equal to what for this expression? Oh, we've got some people doing brilliantly already. Fantastic. And can we work out our units as well? So again, products over reactants, always products over reactants whenever we do equilibrium constants. So our concentration of NO2 gaseous to the power of 2 because it's got that 2 up there. That's the stoichiometric amount, the molar amount, divided by reactants, so NO gaseous, to the power of 2, because there's a little 2 up there to say we need 2 lots of NO. So times by O2 gaseous to the power of nothing, or to the power of 1 actually, technically, but we don't put a power up there because we're lazy and we can't be bothered to put 1. Fantastic, well done. Yeah, don't forget to write the products. Yeah, and then, so that's the expression. Perfect, lovely, thank you very much. Tick. That'll be 1 mark for writing the expression, and then we get another mark for the units. So can we work out those? If you can jump straight to it and you don't need to work it out, writing out the units, then that's brilliant. But if you do need to write it out, then do, because it's totally fine. And I think it's a good check as well. So it's our concentration squared on the top, and then we've got concentration squared on the bottom, times by concentration. So overall, again, we can cancel our mole per dm cubed. So we end up with 1 over mole per dm cubed. And so if we want to write it all on a flat line, the best and easiest way to do that is to reverse the sign of the power. So it becomes mole minus 1 dm cubed, or if we write the positive one first, dm cubed mole minus 1. Okay, do we need to write out state symbols in the expression? So you don't have to, but I would, because technically you should. Technically, by writing out the state symbols A, for those of you that need to do heterogeneous equilibria, you're reminding yourself that this is a homogeneous equilibria, that everything is in the same state, just in case you've made a mistake and included something in an opposite state. So it's a good practice to do it. And we technically should, in terms of our theory. Having said that, you're not necessarily going to lose a mark, so unless you've made like a major error. So don't worry about it, but I would if you could. DM3 mole to the minus 1. So how are we doing? Yep. Lovely. Okay, anybody? What's the difference between Kc and Kp? Kc for concentration, Kp for pressure. So C, concentration for things in a gaseous or liquid state, because you can measure the concentration, moles per unit volume. And Kp, when you're specifically measuring gases and their contribution to pressure. So you can measure you can use gases for Kp, that's fine. You're just using a different, basically different numbers. Should be approximately the same. Yeah, good, well done. Is there any relationship between Kc and Ko? I'm not sure I've heard of Ko. Ka, I know Ka and Kp, and there's lots of Ks, there's lots of equilibrium expressions, but I'm not sure I've heard of a Ko. Okay, so we're doing really well for time. Kp, yes, there is because they're both expressions of the position of equilibrium within a reaction. So yes, Kw, that's another one. Yeah, exactly. So yes, there is a relationship in terms of they're both describing the same thing or similar things, but in different situations. You can't directly relate them to each other, though, I don't think, because they are describing ever so slightly different things. They're both describing the position of equilibrium, but in different ways. Kw is the position of equilibrium that talks about water, how much water has dissociated into its ions. So it's, yeah, Kw is all to do with water and how much it dissociates into H+ ions and OH- ions. That's what Kw is. Okay, let's keep going. So Kc calculations, let's have a go at plugging some numbers in. There's so many Ks, I don't know, because there's lots of practicals and experiments and reactions occur in reversible reactions, and therefore we need to know about equilibrium constants because it tells us where in the equilibrium we are, because that could have a huge effect on how many moles you need to do a reaction, on how fast the reaction is proceeding. In industry, you need to know about your equilibrium of your reaction because you want to know, how you can push to produce more of a product or less of a product, or have the reaction happen faster. So there's loads of Ks, but they're all very, very useful. Okay, so Kc calculations, if we're given equilibrium concentrations, it's a lot easier. If we're given at equilibrium, they're making our life a lot easier. So at equilibrium, there are 3 moles of SO2, 2 moles of O2, and 5 moles of SO3. And the reaction chamber holds 500 centimeters cubed of the reaction mixture. Calculate the equilibrium constant Kc for this reaction. So first step, we're going to need an expression for Kc so that we can plug the numbers in. This is one we've done before, so I'm just going to speed write it out so that we don't waste time. Can you plug in the numbers though? Which numbers do you need and what do we need to have done to those numbers? I'm just going to speed write out our expression for Kc. Products over reactants. So SO3 gaseous squared over SO2 gaseous squared times O2 gaseous. How do we plug those numbers in and what do we need to do? So we're looking for concentrations. These square brackets mean concentration. So at the moment we've been given moles and we've been given a volume. So what do we need to do in order to plug these numbers in? We need to work out our concentrations. So you could plug it in, you could create like a little table if you wanted to, but we do need to work out our concentration, which is moles per unit volume. Concentration is moles per volume, but our volume needs to be in decimeters cubed. We measure concentration in decimeters cubed. That's our standard unit. So we're going to need to convert, because we've got centimeters cubed. So 500 centimeters cubed. How do we convert to decimeters cubed? What's 500 centimeters cubed in decimeters cubed? Divide by 1,000. Good. And hopefully that's something that you are used to and you've remembered. If not, get that in your head because it's something we use so often in A-level chemistry. Divide by 1,000 to go from centimeters cubed to decimeters cubed. So let's plug in some numbers in. We need concentrations, which is moles per volume. So for the top, we've got SO3, which is 5 moles, divided by 0.5 decimeters cubed. Mole divided by decimeters cubed, moles per decimeter cubed, all squared, divided by SO2. There's 3 moles of SO2 in 0.5 decimeters cubed, all squared, times by 2 moles of O2 divided by 0.5 decimeters cubed equals, what's our value for Kc? Capital K, little c is yeah, good. Well done, Manek. That looks good. Oh, so I got something different in front of me. Let me plug it into a calculator again. In case. Yeah, okay, good. Sorry, I got 0.69. Mole and units. What are our units? It's moles over moles. Mole per decimeter cubed squared divided by mole per decimeter cubed squared times mole per decimeter cubed. So we must make sure we write in our units. Our units should be mole to the minus 1 decimeters cubed, or decimeters cubed mole to the minus 1. I'm going to write it that way around. Yeah, 0.694. Lovely, but I'm only going to write it as 2. Well, I mean, I could write it as 3 decimal places, but we've only really been given 1 significant figure in the answer. So to be honest, if this were an exam question, they couldn't really expect us to give it to any more than 1 significant figure, because that's all we were given, 1 significant figure in the question. Lovely. So where's the equilibrium lie then in this case? Where is the equilibrium at the moment? Kc is less than 1. So our value good, towards the reactants. Kc is less than 1. Equilibrium lies towards the reactants, or to the left. Good, well done. Fantastic. Okay, let's keep going then. So if it gets a little bit harder, or we can make it a little bit harder, we're going to try and speed through this question as well. If we're given initial concentrations, we have to do a little bit of faffing. Now, I'll spend some time on this one. It may mean we don't have time to spend as much time on the exam question, but this is where people tend or can get a little bit confused. So if we've got 18 moles of methanol to begin with and 12 moles of carbon monoxide, they were added to 300 centimeters cubed in a reaction chamber. Yes, so we're going to need an ice table. At equilibrium, there are 5 moles of ethanoic acid produced. Calculate the equilibrium constant. So we're going to need an ice table. So the way that I tend to set these out, and I'm going to annoy myself and take up loads of space, but oh well, it's easier to see this way, is write out your equation, or if you're given to it in the question, you can just write below it. That's also useful. And then we can write ice. What does ICE, ice, stand for? What does ICE stand for? Those of you that have done one of these tables before, and they're very useful in Kc, but also in other aspects of equilibrium as well. Initial change equilibrium. So what is the initial concentrational moles? What is the change in concentrational moles? And therefore, what is the equilibrium concentration? That's what we're going to be working out. So let's write in, I'm going to write in yellow, I'll stay in yellow actually, what we're given in the question. In the question, we've been told 18 moles of methanol and 12 moles of carbon monoxide are added to a 300 centimeter cube reaction chamber. So I can immediately write in some numbers. So I've written 18 moles of methanol, 12 moles of carbon monoxide, and 0 moles of ethanoic acid. You have to practice working out what these questions are telling you. This question is telling me I started with methanol and carbon monoxide and added them to a reaction chamber. So I started with no ethanoic acid. You have to get used to working out if that's what they mean in the question, because they don't always specify. Okay, so if I started with 18 moles, actually I'm going to write that a bit bigger, and 12 moles of CO2, and then I had no moles of ethanoic acid, and then it says at equilibrium there are 5 moles of ethanoic acid. Okay, so at equilibrium, in the equilibrium box, I can say there were 5 moles. So how much has it changed by? Now I'm going to do some deduction work. That's the information I was given in the question. Now let's do some deducing and work out what's happened. I'm going to do it in green. So how has it changed? Well, to go from 0 to 5, I must have gained or added or produced 5 moles of ethanoic acid. So I've had positive, and I like to put the pluses and minuses in because I think it helps. So we've added 5 moles of ethanoic acid. Looking back at this expression, or the balanced equation, if I've gained 5 moles of ethanoic acid, what must have happened to my moles of methanol? How many moles of methanol must I have used up? If I've gained 5 moles of methanoic acid, I must have lost 5 moles of methanol and 5 moles of carbon monoxide, because it's a 1-to-1 ratio. In order to produce 1 mole of ethanoic acid, I have to have used up 1 mole of methanol and 1 mole of carbon monoxide. So to produce 5 moles of ethanoic acid, I have to have used up 5 moles of methanol and 5 moles of carbon monoxide. At this point, if there were different stoichiometric numbers, if there were different reacting ratios, you might have to adjust for it, but in this case, it's 1 to 1 to 1, so it's nice and easy. So I must have, therefore, 13 moles of methanol left. Because I've used up 5 moles, I must have 13 moles left. I started with 18, I've lost 5, so I've got 13. That's why I like to put the minuses and the pluses in, because it reminds you to take away the number or add the number. And for carbon monoxide, I've therefore got 7 moles of CO, of carbon monoxide. Good, well done. So I've got my equilibrium amounts. I know now how many moles of each I have at equilibrium. So I can do the same thing that we just did on the previous slide. I can write an expression for Kc, products over reactants. So concentration of ethanoic acid, over the concentration of ethanol times the concentration of carbon monoxide. I'm being lazy and I'm not putting in the gaseous numbers. I'm just very aware of the time, so apologies. But because they're concentrations, I need to plug in numbers that are concentrations. At the moment, I've got moles. How do I turn it into a concentration? Well, I've been told the volume. So 300 centimeters cubed is, again, it's got to be in decimeters cubed, has to be in decimeters cubed, because we're talking about concentration. So 0.3 decimeters cubed. So I can plug in all of my numbers as concentrations. So in this case, it will be, where's the ethanol? 5 moles divided by 0.3 decimeters cubed, divided by, mole is an amount of substance. It's like saying dozen. It's like saying a grand, a score, a pair, a couple. It's just an amount of substance. This, so that one's 13 moles. And it has a specific value, which hopefully you guys know about. 7 moles divided by 0.3 decimeters cubed. So Kc in this case is equal to, no worries. Good, well done, Catherine. Yep, lovely, well done, Zara. I got something similar as well, 0.016 something. I think I got 1.165, and units, we need to check the units. Well, one lot of units will cancel another lot of units, so we end up with 1 over mole per decimeter cubed, or decimeters per mole, decimeters cubed, sorry, moles to the -1. Well done, fantastic, Leona, as well, good. And in a question like this, you would probably get 1 mark for the expression, 1 mark for your answer, 1 mark for the units. And if they're feeling nice, because you have got a lot of work, you might get 1 mark for your equilibrium amounts as well. So these questions can be 3, sometimes 4 marks, which is nice. Well done, guys, good. Okay, we're doing well for time. Hopefully we can now spend 5 minutes on the exam question. How is everyone feeling about that? Anybody not happy or got any questions? Anything, any steps of that? Yeah, let's go back and just super quick talk through the ICE table. So it's a really good way of working out what's reacted and what hasn't. So I'm looking at the amounts of each of my different reactants and products at equilibrium. The key thing I'm interested in is the equilibrium amounts, because I'm talking about at equilibrium. I want to find the equilibrium constant. So it's an equilibrium constant. I want to find the position of equilibrium at equilibrium. So I can't use any of my initial numbers because I don't care what happened at the beginning. I want to know what's happening at equilibrium. So I use my ICE table to work that out. Read the question, find out what information they've given you in the question. So they've told us about our starting amounts, 18 moles of methanol and 12 moles of carbon monoxide. And they've told us, so therefore we started with no ethanoic acid. Sometimes you have to read into the question to work out that. Sometimes, like in this case, they don't tell you explicitly. So you have to make that assumption. And that's okay, we can make that assumption. And they then tell us at equilibrium, there are 5 moles of ethanoic acid. So I can put those numbers in immediately into my table. the initial values, I, and then the equilibrium value of ethanoic acid. And then I can work them out. Yes, I think they are the same thing. Yeah. Yeah, good. And then I can work out the rest. So the first one I did is where I've got 2 pieces of information and I can fill in the third. So how did I go from 0 moles to 5 moles? Well, I gained 5 moles of ethanoic acid. If I've gained 5 moles of ethanoic acid, I must have lost 5 moles of my reactants because it's a 1-to-1 ratio. Yes, the equilibrium moles down here is the 13, the 7, and the 5. Because I've worked out that I must have lost 5 moles of methanol and lost 5 moles of carbon monoxide. So at equilibrium, when I've got my 5 moles of ethanoic acid, I've only got 13 moles of methanol and 7 moles of carbon monoxide because I've used 5 moles of each to make the ethanoic acid. Yes, good. So Alex, try and refresh your page maybe. So I think it's really useful in working out what's happened. I mean, you don't have to use it. You can just think it through and work it out without using a table, but you're basically doing what's in the table anyway. And I think it's quite a nice way of setting it out, laying it out, quite visual. And, you know, for example, when you've worked out we've lost 5 moles. So then we've got, you know, in both cases, we've got 2 pieces of information and we can easily work out the third. It's just a puzzle then, isn't it? Okay, so let's try. Yeah, I think so as well. Is equilibrium about balancing equations? Not really. You do need to do balanced equations. You need to be comfortable with balanced equations, and they are involved in both, but they're not we don't really balance equations. They're already balanced basically, or they should hopefully be already balanced. These web classes happen once, well, we do an A-level web class every Sunday and it just rotates between physics, maths, chemistry, biology. I'm going to pop a YouTube timetable on in a couple of minutes to show you. Right, I need to speed up so I've got time to show you the website and everything at the end and talk you through the rest of our timetable, etc. So let's have a go at this exam question. So they're written a little bit horribly. You have to find the information first. So it says hydrogen and iodine react together in a reversible reaction as given. The chemist mixes together 2 × 10⁻³ moles of hydrogen and 4 × 10⁻³ moles of iodine in a 1 decimeter cubed container. The chemist seals the container and the mixture is heated and left to reach equilibrium. At equilibrium, the mixture contains 3 × 10⁻⁴ moles of hydrogen. Calculate the equilibrium constant, including units, if any, for this equilibrium. Give your answer to 3 significant figures. So let's set up an ice table as quickly as we can. So H2 plus I2 goes to make 2HI. So it's not all a 1-to-1 ratio here. There is going to be a little bit more of ratio maths needing to happen. So then we can do initial change equilibrium. And we can write in our initial amounts. Obviously, once you get comfortable, you don't have to write in initial change equilibrium, but some of us aren't quite as comfortable, so I'm going to write them in for us. Initial change equilibrium. So again, what information have I been given from the question? I've mixed together 2 × 10⁻³ moles of hydrogen and 4 × 10⁻³ moles of iodine. So therefore, I must have no moles, 0 moles of HI. Yes, exactly right. Good spot, chemic medic. Well done. You do make that assumption. You assume it's a closed system because we've sealed the container. No mass can get out, so we're not going to lose any gases. Exactly right. Yeah, well done. It is a closed system. Therefore, equilibrium will be reached. They're just saying that in order to cover their backs. Hopefully, they wouldn't say anything to the contrary. They're not going to try and trick you, but they're saying that just to be sure that it's a closed system, so that it's going to reach equilibrium. Then it says at equilibrium, the mixture contains 3 times 10 to the minus 4 moles of H2. Okay, so we're not looking at products this time. They haven't told us about products. They've told us about our H2. So what's the change then? How much have they changed by? How much has it changed by? It's gone from 2 times 10 to the minus 3 moles to 3 times 10 to the minus 4 moles. So we can work out, we've only got one piece of information missing here, so we can work out what that information is. How much has it changed by? If I do 2 times 10 to the minus 3 minus 3 times 10 to the minus 4, I can work out it has changed by, we've lost 1.7. Oh, lovely, well done, random facts, that's good. No, they wouldn't, that's what I'm saying, ChemicMedic, they wouldn't say, ChemMedic, they wouldn't say they didn't seal the container unless they then wouldn't go on to ask you to calculate KC. If they said they didn't seal the container, they might then go on to ask, why wouldn't it reach equilibrium? So you could talk about it not being a closed system, but they wouldn't ask you to find KC, because you have to have equilibrium to find KC, and you can't get an equilibrium unless you've got a sealed container. Cool, so what's the change? Well, we've lost 1.7 times 10 to the minus 3. So if we've lost 1.7 times 10 to the minus 3 moles of hydrogen, then that must mean, because it's a 1 to 1 to 2 ratio, so we must have also lost 1 times 10 to the minus 7, sorry, 1.7 times 10 to the minus 3 moles of iodine, because they react in a 1 to 1 ratio to produce our product. And then how many moles of HI have we produced? Therefore, how many moles of HI have we produced? It's a 1 to 1 to 2 ratio. So if we've used up 1.7 moles of hydrogen, good, we must, well done, fantastic. We must have produced twice as much HI. So that's, oh no, sorry guys, I pressed a button without meaning to. 3.4 times 10 to the minus 3. I'm running out of time. I need to speed up a little bit. Moles. So then we can work out, well, we've gained 3.4 times 10 to the minus 3 moles of HI. So our total moles, because we started at nothing, will be 3.4 times 10 to the minus 3. Our total moles of iodine is 4 times 10 to the minus 3 minus 1.7. So that gives us 2.3 times 10 to the minus 3 moles left at equilibrium. So we've then got all of our equilibrium amounts. We've got all of our equilibrium amounts, so we can just plug it into the equation. I've noticed we need a volume, but what's our volume? We need a concentration, sorry, but what's our volume? It's just 1 decimeter cubed. So actually, when I plug my values in to the equilibrium expression, I'm dividing by 1 every time. So I don't actually need to do anything to those values because I'm just dividing by 1. So what have we got? KC, again, products over reactants, so concentration of HI. Again, I'm going to be lazy because I'm running out of time and not writing the units. Concentration of HI squared time over the top of concentration of H2 times the concentration of I2, both to the power of 1. So let's plug in some numbers. So my concentration of HI is 3.4 times 10 to the minus 3 needs to be squared over concentration of H2, so 3 times 10 to the minus 4 times I2, which is 2.3 times 10 to the minus 3. And if I just want to prove to myself, I can just prove to myself the concentration is moles per volume, and my volume is 1. So these are concentration values because I've just divided by 1 in all of them. Sorry, I've written that really small because I didn't write it in the first place. So what's my value for KC? I have got 16.8, well done. And no units because it's mole per dm cubed squared divided by mole per dm cubed times mole per dm cubed. So they cancel completely. Good. So we end up with 16.8-ish. if we round up. It says to 3 significant figures, specifically asked for that, so they will not take an answer that is more significant figures than 3. So 16.8, no units. You can write no units if you want to be safe, but you don't have to, you just give no units. Actually, no, I would. No, I've just read the question. It says including units, so I would say no units, so that you're showing your examiner you haven't just forgotten, you know there's no units. So 1 mark for your answer, 1 mark for the expression, and then 1 mark for your kind of calculations. Right, we're going to need to speed on. Okay, yeah. So yeah, the units are entirely dependent on, you know, how many of these things are squared or not squared or whatever. Because if you change the number of concentrations you've got, you're therefore going to change the units. So you just practice. Okay, so hopefully we can now understand the quantitative assessment of the position of dynamic equilibrium. We can work out the units for the equilibrium constant, and we might need a little bit of practice to do that. Sorry, just moving that over so that I can use my mouse. And we need to calculate the equilibrium constant, or we can calculate the equilibrium constant from initial and equilibrium conditions. If you have any questions, pop them in the chat, but I'll just show you now. These are our upcoming web classes. So we have got A-level biology next Sunday. Then the week after, we've got another chemistry web class. Then we've got physics after that, and we've got biology after that. They should be on our in our like in the upcoming section of our YouTube what's it called, profile. So please feel free to head over there. You'll also find all of our previous YouTube classes, A-level Sunday sessions on there. So please feel free to go back and watch through those. You should also find all of our slides and stuff as well. So please feel free to download them, take them away with you, use them for revision. It's always products on the top of the reaction. Always, always. For equilibrium, it's always products over reactants. So that helps. And so one thing that we have on our website is our courses. So the courses is basically everything you might need to succeed at your A-level. We have got revision videos that cover all of the content, that clearly explain every single specification point so that you know you're covering everything. We've got quizzes that are interactive so that you can test your knowledge, you can do multiple choice questions, you can check your answers. And we've got revision guides, which are everything in the specification condensed into easy, fun, interesting content with lots of nice images that help with your understanding. We've got exam walkthrough videos that talk through different exam questions and how to do them. And we've got other exam packs as well, where we look at exam questions that we think might come up or things that are often come up, and we plug in different numbers, and you can have a go at all of those as well. So I'm going to pop over onto that and have it show you what the website has got available. But if you're interested, then we have an offer on at the moment, which is 25% off if you use the code BACKTOSCHOOL21, all capitals. If you plug that in at checkout, then you'll get 25% off the first month. So you can have a look, see if it seems like your thing. There's so much content on there. And one of the things that is included in the courses is the web classes. So you get access to loads of web classes every week. For chemistry, we have 1, 2, 3. We have 5 web classes every week, 3 on content and 2 just exam questions. So let's go and have a look at what that involves. I'm going to stop sharing this and start sharing. Oh no, apart from when my laptop gets cross at me. There we go. And start sharing. Whilst this is being slow, I'll just answer your question. Quick question from experience: which example of A-level chem do you think is harder, OCR, AQA? It's entirely dependent on the student. Oh, sorry, my laptop's being nice and slow. It's entirely dependent on the student. OCR can be very fussy about the keywords that you need to use. but they also don't cover, AQA has a bit more of a broader subject. I really like AQA. I think it's much more about preparing the student for using chemistry in life. OCR and Edexcel are, in my opinion, because obviously this is just my opinion, a little bit more, let's answer the exam question exactly how we want it so that you can pass the exam. So it's entirely up to you. So just to show you, hopefully you can see my screen. You can have a look on the website as well. Please feel free to go and have a browse. But if you were interested in doing our courses, so you could, what we have available on the courses is a load of content. You can see it shows you the course progress, so you can see how much of the content you've looked at already. You can have a look at, if you click on, for example, go on to atomic structure, you can see we've got videos, we've got the exam pack, so lots of information, questions, we've got the revision guide, we've also got all of our, down the side here, you can see, oh, that's going to start playing now, stop. You can see we've got all of the videos that you can watch, we've got questions that you can watch, that you can have a go at, etc. And it tells you what you've covered and what you haven't. And then you can see here at the top, we've got a nice banner as well, but you can see we've got web classes. And so we offer web classes and drop-ins. So if I show you those super quickly. So at the moment, we've got our web class coming up. So it shows you can have a look at the schedule. We have loads of web classes every week. We have drop-ins, which is basically where we go through loads of exam content, and it's all amazing. So if you'd like to have a go, please use the code BACKTOSCHOOL21, gives you 25% off the first month. But thank you so much for being awesome. I'm going to head off now, but you've been brilliant, and I will hopefully see you very soon. Thanks very much, guys. I will see you very shortly. Have a lovely rest of your weekend. Thanks, guys. Well done.